All right, let's get into it. Today, we're going to crack open a classic linear algebra exam problem. You know the kind. It's not just about can you do the math, it's about do you really get what's going on with subspaces and transformations. So, let's dive in.
So here's our game plan. We'll set up the problem, then we'll solve the subspace riddle in part A. After that, things get interesting with part B. We'll prove why the images are the same, but then show why the kernels are totally different. And we'll wrap it all up with the one big idea you need to take away from this.
Okay, so this is the beast we're tackling today. Question 3. Part A is your classic subspace puzzle, but part B, that's where it really tests your intuition. It digs into what a matrix representation really means. This is all about connecting the dots, not just crunching the numbers.
All right, let's kick things off with part A. I like to think of this as a kind of riddle. We've got these two subspaces, and we need to find the one magic value that lets one fit perfectly inside the other.
Meet our two main characters, U and W. U is pretty straightforward, right? It's all the vectors in four-dimensional space where the first coordinate equals the third and the second equals the fourth. Easy. But then there's W. And W has this little mystery variable A baked right into its definition. Our job is to figure out what A has to be. So here it is, the big question for part A. What value of A makes it so that every single vector that belongs in U also belongs in W? How do we make sure every resident of U is also a resident of W? Now, we could try to check every vector in U, but, there's an infinite number of them, so that's not going to work. The smart way, the work smart, not hard way, is to just check the fundamental building blocks of U, its basis vectors. If the basis is in W, then everything built from that basis has to be in W too.
Finding a basis for U is actually pretty simple. The rules are x equals z and y equals t. That means any vector in there has to look something like this, z, t, z, t. See how that works? And if you just pull out the z's and t's, you can see the whole space is just spanned by two simple vectors, 1, 0, 1, 0, and 0, 1, 0, 1. And there's our basis.
Okay, this is the key moment. We just need to take these two basis vectors and make sure they play by W's rules. If they satisfy the condition for W, then the entire subspace of U will too. Let's plug them in and see what shakes out. So check this out. For our first basis vector, U1, we plug it into W's equation, and it simplifies down to a squared minus 1 equals 0. Nice. For our second vector, U2, it simplifies to something even better, a minus 1 equals 0. Now here's the kicker. For U to be completely inside W, A has to satisfy both of these equations at the same time.
And just like that, the answer kind of reveals itself, doesn't it? The first equation, a squared equals 1, tells us a could be 1 or negative 1. But that second equation, well, it's pretty insistent. It says a has to be 1. So what's the only value that works for both? You got it. A equals 1. Part A, solved.
All right, take a breath, because now we're heading into part B. And this is where things get a little sneaky. On the surface, it looks pretty simple, but there's a subtle and absolutely crucial twist. It's all about what a matrix is really telling you. So here's the scenario. We have two transformations, T and S. And hey, look at that. Their matrix representations are identical. You might think, great, they're the same thing. But not so fast. You gotta read the fine print. T is defined with an input basis B and an output basis D. But S, it uses a different input basis, C. The output basis is the same, but their starting points are different. That one tiny detail changes everything. This leads us to the two big questions. If their matrix blueprints are the same, are the transformations themselves basically the same? To be specific, is the image of T the same as the image of S? And what about the kernel, the set of vectors that get sent to 0? Are those the same too? Let's find out. First up, let's look at the image. Are they equal? Well, the answer here is actually yes, and the reason all comes down to that shared output basis. Think about it this way. The matrices are identical, so their column spaces have to be identical. Now, what is the column space? It's basically a recipe. It gives you the coordinates for the vectors that span your image. And since both T and S are using the exact same cookbook, that output basis, D, to turn those coordinates into real vectors, they're going to bake the exact same cake. The images have to be identical. Okay, so the images are the same. Then the kernels must be the same too, right? Nope, this is the trap. This is where those different input bases come back to bite us. The claim is false, and the best way to prove it is with a really simple but really powerful counterexample.
Let's keep things simple and work in good old 2D space. For basis B, we'll just use the standard guys, 1, 0, and 0, 1. For basis C, we'll get a little tricky. We'll use the exact same vectors, but we'll just swap their order. And for our matrix, we'll use this really simple one that just projects everything onto the x-axis.
Okay, now watch this, because this is the whole point. To find the kernel, we find the null space of the matrix. For both T and S, that gives us the same coordinate vector, 0, 1. But what does that coordinate vector mean? For T, on the left, it means 0 times its first basis vector plus 1 times its second. That gives us the vector 0, 1, the y-axis. Now for S, on the right, we do the same thing, 0 times its first vector plus 1 times its second. But remember, we swapped them, so that gives us the vector 1, 0, the x-axis.
And there you have it. The kernel of T is the y-axis, the kernel of S is the x-axis. Are they equal? Not even close. The claim is absolutely, definitively false.
So, after wrestling with all of that, what's the big lesson here? What did this problem really teach us? It all boils down to one of the most fundamental ideas in linear algebra: context is everything.
Let's just sum it up. The images were the same because they were being described from the same point of view, that shared output basis D. But the kernels were different because the instructions were being applied to different starting materials, those input bases B and C. The huge lesson is that a matrix on its own is just a grid of numbers. It's meaningless until you know the context, the bases that it's operating on.
Which leaves us with one final, crucial thought. The next time you see a matrix representing a transformation, what is the absolute first question that should pop into your head? The answer, of course, is with respect to which bases. Never, ever forget to ask about the context.